Yeah, so GPU accelerated Zarr. Given the audience, this is going to be like 90–95% GPU stuff. Uh, Really, the only thing you need to know about Zarr storage format for in-dimensional arrays. So you have some big array, break it up into chunks, compress those chunks, and then save those out to disk. So gonna skip past the Zarr thing just for time, but I'm gonna mention something new in Zarr version 3, if you haven't used it, is this concept of shards or sharding. So you still have that same outer array, that's your in-dimensional array that you're working with. You still have those same inner chunks that are smaller bits of the array. But with shards, the idea is you take a bunch of those chunks, compress them each individually, and then take those compressed bytes and stick them together end to end. And that's the thing that you write out to disk, either to local disk or object storage or whatever. So kind of breaking that link between the chunk and what's on the file system. This is great for multiple reasons, but for the GPU specifically, it's nice because it gives us an additional layer that we can parallelize using all those nice GPU cores. So we're going to be using shards for this example here. I'll just like very briefly mention that if you want to get started with GPU accelerated computing and you happen to have an NVIDIA GPU, it's just a one-line change to Zarr Python specifically. So with this one-line change to enable GPU stuff, some settings get adjusted in the background such that when you slice an array, you get back a CuPy indie array. So typically you'd get back a NumPy indie array. CuPy is a project that builds on top of CUDA and uses like NVIDIA GPUs to have the data on the GPU and GPU memory and do all the computation with GPU kernels. So one line change to get started. We'll talk for basically the rest of the talk will be like why this might not be exactly optimal and what we can do to make it better. Um, Brief bit of background on GPUs if you haven't used them before, don't have a ton of experience with them. They are really, really, really fast for the right kind of problems. We're going to be doing matrix multiplications as like our simulated work. They're very fast at matrix multiplications. They're very fast at lots of different things, though. Um, they can be a bit complicated to use. So, first of all, usually, not always, but they usually have a separate memory hierarchy from what you're used to. So, maybe, so on you have these two concepts. You have the host, which is like your CPU, that's where your Python program is running. It has its own set of memory. And then you have your device, which is like the GPU, the accelerator, which often has its own separate memory hierarchy that is separate from the host memory. This memory is relatively fast, so you can get data from the GPU memory to the GPU cores pretty quickly. Um, but it can be relatively small, at least compared to what's available through for like host memory systems. You can get machines with like a terabyte of memory or whatever. So relatively fast, maybe relatively small. The bigger thing really is the link between host and device memory can be relatively slow. So if you're using something like PCIe, you have like a theoretical maximum bandwidth of whatever, 128 gigabytes per second. So that can be a bottleneck. If you're trying to move a bunch of data, if you're moving data too much, like back and forth, that can be a problem. So for the most part, we're going to be trying to keep our GPU busy for a Zarr workload, just by being really careful to keep it fed with a lot of work to do. We're not going to be talking at all about like actually writing functions, kernels that run on the GPU. There's lots of ways you can do that, but we will only be focusing on like data movement and using existing kernels, like the matrix multiplication that's available through CuPy, doing that efficiently. Um, I want to take like a minute or two to talk through like programming models. So how does your like code here relate to what's actually happening on the hardware at an extremely high level? So first of all, on the CPU, things are ignoring threads, ignoring things like async IO. Things are pretty straightforward. So you have some function that runs, it completes, and then control flow returns to your program, and you move on to the next stage. So you do your read, that runs, it completes, move on to the transform, and so on. So nice linear flow there, no surprises. With the GPU, things are immediately a bit more complicated. So we do have these two sides. We have the host side, that's what's running on your CPU. So this would be like our Python program running on the host. And then you have your device side. So what is actually happening on the GPU hardware? So we have those two concepts. And then the thing to note about not all APIs for programming GPUs, but many APIs are going to be like asynchronous and non-blocking on the host. So when we call a function like this hypothetical read chunk, that's going to do some work on the host to kind of like set stuff up. And then it might, queue up, schedule some work to happen on the GPU. But we're not going to wait around for that work to complete. So we're just going to do this work on the host. And as soon as that's ready, as soon as it's dispatched the work to the GPU to do, we're going to carry on. So our program will move on to the second read chunk. And, again, we're not going to wait around for that second read chunk. We're not going to wait around for the device at all to do anything. We're just going to keep on going and, transform the data, which is like maybe a little weird because now we're calling this transform on this read, which maybe hasn't finished yet. So again, it can be a little weird at first, but at some point, things will happen. If you ever do need to bring these back into line, different systems will have different APIs for this, but in CUDA land, it's called a synchronize. So we synchronize the host and the device, which basically blocks on the host until everything that's been queued up on the device has completed. Um, so anyway, just like no, it's like we're going to be using these kind of non-blocking APIs to make sure that multiple things are happening at the same time. And it can be confusing to tie that back to what's actually like in your Python code or C++ or whatever you're writing. Last thing I'll mention, last little primitive that we're going to be using a bunch of are CUDA streams. So again, different runtime hardware systems have different names for this, but in this case, it's a way to express additional concurrency that's available in your program to your device. So in this case, our A's and B's are kind of independent. They're like blockwise operations. They don't interact. And so if we do have some way to express that in the program. All of the stuff that happens like on stream A has to happen in this order. We have to read before we transform the data. Likewise with what happens on stream B, we have to read before we transform the B. But those two, that A and B, can happen in any order. We don't really care what order it happens in. And so with CUDA streams, you can express that kind of logical correctness requirements that your program has and then leave it up to the GPU to decide exactly how it's going to, what order it'll execute those in, depending on like which resources are currently in use and available. And so we're going to be using that extensively in this Zarr workload in order to make sure that multiple things happen at the same time. Cool. So brief summary. We're not going to talk about like authoring kernels and getting the most out of like warp specialization or anything like that. We're just going to be talking about like how to keep your GPU busy, how to avoid blocking the GPU. We're going to be using those non-blocking APIs and CUDA streams quite a bit. The workload is like I think, somewhat realistic workload for some Zarr things, not everything. We're going to be doing things at the shard level. Again, the idea is like you have maybe some like you're applying some ML deep learning model, or maybe you're training it, and you can operate one shard at a time. That's not going to be all workloads, but I think a decent number could be thought of that way, or parts of workloads could be thought of that way. So we're going to load in a shard of data. In order to use the data, we have to decompress it. That'll be done on each chunk. And then we're going to perform a bunch of matrix multiplications, which is just a stand-in for some moderately computationally expensive thing. If you're not doing something that's computationally expensive, then maybe it probably doesn't make sense to even think about using GPUs if your compute isn't the bottleneck anyway. The actual sizes here, I think the only relevant things here, we have like a decent number of chunks per shard. I didn't tune these numbers at all, but kind of thinking something more than the number of cores that you have available on your machine, just for this benchmark, but decent number of chunks per shard. The shard needs to fit in memory, so that's like our unit of work. So that has to fit in either host or device memory. Pretty, whatever, 400 megabyte size shards here. The array the entire array would happen to fit in either host or device memory. It's only 3 GB, but that's not like relevant for this benchmark that we're going to be looking at. Okay. I'm sure everyone's eyes are like immediately drawn to this table. There's so many caveats around this number, so just ignore these numbers for just a second. But we are going to be comparing three different workload implementations of the same workload. So the first workload here is going to be using your stock Zarr NumPy. So it's going to be using Zarr's IO pipeline, which is I'm just using a local disk here. But it's using regular old Python for reading data from disk. It's using numcodecs for decompressing the Z standard compressed data, and then it's using NumPy for the matrix multiplication. The Zarr the second implementation here, is the same, except we've set this enable GPU thing. So again, we're using Zarr for the IO pipeline, numcodecs for the decompression, so that's still happening on the host. And then there's the host to device transfer that kind of happens in the background by CuPy, and then using CuPy for the matrix multiplications. Okay, so you can look at the numbers, and yeah, more or less all this says. So everything's the same. It's just saying it's just the matrix multiplication library doing that is happening on the GPU now, and that's fast. Like not a huge surprise there. This is expensive enough that it's worth doing the host to device transfer. So this is doing additional work to do that transfer. But I was curious, like, it's faster, but is it actually fast? And so basically use some tools that NVIDIA provides for profiling GPU workloads to see like, are we, what is the GPU actually doing? How's our utilization? What are the bottlenecks? And basically kept on working on this custom pipeline that avoids all those bottlenecks to see what could we actually get to if we really tried to optimize this. And that's where we get to this lower number here. Again, the absolute values here don't matter. The relative numbers, I think, aren't even that meaningful. I think the interesting thing is like, is there a gap here? And apparently there is. So there are some bottlenecks in what you would get out of like a standard Zarr config enabled GPU. So that's what I want to spend the rest of the time on, is actually going through that as like a demonstration of what it takes to optimize some GPU accelerated code, and some things that we might be able to bring to Zarr Python so that you can use libraries that do these things for you. Okay. Also want to mention, these are some older numbers. Davis has been doing a bunch of work recently to improve the IO pipeline in Zarr Python. So lots of grains of salt. Cool. So yeah, we're going to be stepping through some code here shortly, and some profiles, but at a high level, we're going to have a few different strategies for making this pipeline fast. So the pipeline itself is going to keep using Python for IO, still reading data into host memory. But instead of decompressing on the host and then transferring, we're going to transfer the compressed bytes over to the GPU, which is great because the compressed bytes are smaller, and that host to device transfer can be a bottleneck. So we're transferring fewer bytes, but that does mean we need to decompress the bytes on the GPU. That can also be a good thing. If your GPU is idle anyway, just waiting for data, you might as well use it to do the decompression. And that decompression itself can actually be parallelized, because at the very start we said we were using sharding to make decompression faster, parallelizable. So we're going to be using really careful with memory. So memory allocations, depending on the workload, memory allocations can be a bottleneck. So we're going to be careful on both the host, including like the type of memory we use. We'll talk about that in a second, and the device, to not make any memory allocations inside of a hot loop. And then we're going to be really careful to use CUDA streams to overlap I/O, host to device transfers, decompression, and compute. Just so that we have CPU cores, we have the disk, we have the device. The device has multiple parts. It has like a memory controller. It has the actual compute cores. We want to make sure that we're using all of the resources that we have available to us. Okay. So next few slides will have some code on the left here, and on the right we'll have some Insight Systems profiles. So first of all, the code, and then I'll show you how to read these. First thing to note is ahead of time, we've like asked our storage system, hey, how big are the shards? And maybe we like find the largest shard, or anyway, we do something ahead of time to know how much memory we need on the host. This is maybe okay as long as you don't have too many shards. That's another way that shards help is it doesn't explode the number of files on the file system or objects in the object store. So this is probably a reasonable thing to do, but ahead of time we allocate some memory for our compressed bytes on the host. We are using this special type of memory called pinned memory. That's just a flag that gets set on that region of memory so that the operating system doesn't page it behind your back in case like it's the OS is running out of memory, low on memory, it might swap to disk or something. We don't want that because we want our GPU to be able to directly access that memory without involving the operating system. Just directly access it so it can copy it over to the device. That speeds up the hosted device copy, which we'll see next. And then the actual read itself is just standard Python. So we're using Python's open, nothing fancy here, and reading into that pre-allocated host buffer, which we then reuse later on. So as far as what's happening over here, so this is an insight profile. At the top, you have things that are happening on the GPU. So under the CUDA hardware, probably too small to see, but this is what's going on in the GPU, which for the first shard is nothing. So right now the GPU is idle. Kind of makes sense since we're using the CPU, the host, to do the actual reads here. NVIDIA does have a thing called GPU direct storage for basically reading directly to device memory. I didn't have a chance to try that out. Someday I will. But for now, we're just using the host for reads, and this doesn't end up being the bottleneck, so it's fine. But for subsequent shards, so this read takes 20 milliseconds or whatever. But while the CPU is busy doing that, now you can see that up here our device is busy doing a decompression on some previous shard worth of data. So we are able to overlap some compute with I/O for subsequent shards. So we've got compressed data to the host now, right? Now we need to copy those compressed bytes from the host to the device. So again, device buffer has been a pre-allocated array. It's the same size, roughly. We didn't talk about how sharding's implemented, but it's basically the compressed bytes stuck together, and then there's an index on the beginning or end that tells you offsets and sizes, things like that. Anyway, we've got a pre-allocated device buffer, and then the only thing that we're doing on the host here is this dot set call from CuPy. That's just scheduling the CUDA mem copy from the hosted device. Okay, so it's way too small to see, I know, but the set here, which happens on the host, is this tiny little thing. It takes like microseconds, no time at all. And that expands out into this much larger mem copy operation that is running on the device. So you can see that's here in teal. So in Insight profile land, teal means a memory operation. And then this bluish thing that's above here, that's a compute kernel. And this happens to be a matrix multiplication. That's for some previous shard. So this shows that we're overlapping host to device copies, which is like utilizing the GPU's memory controller system. We're able to overlap host device copies with compute functions, which is great. Last thing to mention is since this host buffer is pinned or page locked memory, that host device transfer is going to be even faster than it would be otherwise. I think I was running at like 50 or 60 gigabytes per second on the system I had access to. I don't know. It wasn't the bottleneck at that point, so I stopped looking. Next thing to do. So now we have compressed bytes on device, right? We need to decompress them. I personally don't know how to write a Z standard decoder, but for NVIDIA CUDA land, we have NVComp is the library that implements that. NVComp provides a Python API along with a C and C++ API. I had to write a really, really simple wrapper on the C API to get a couple things. First of all, I wanted a non-blocking API. So right now, parts of the Python API, when you access an array attribute or something from the NVComp array, it does a blocking synchronize, which kind of broke the pipeline's performance. And the C API gives you a bit more control over memory allocations that aren't yet exposed to the Python API. Reach out to me if you run into similar issues. We can chat about them, or you can look at the code at the end. I'll share, and there's an issue discussing this, but For now, we have this very, very simple wrapper around the Python, around the C API, and we build up a bunch of buffers here. So one buffer per chunk in this shard by taking slices out of the device buffer that we're doing the copy into. And then we're able to decompress directly into the output buffer. This isn't always possible. It's only possible if the shards are, no, the chunks are contiguous in the shard, I think. There might be a need for a temporary allocation in general, but if not, in this case, we were able to decompress directly into the output array for that shard. This is showing this insight profile is showing the overlapping, or sorry, the non-blockingness of this decode. So here we have the decode thing. Our host immediately moves on to doing the compute, which we'll see next. But while it's doing this on the host, this decode here has been expanded into these decompression kernels that are running on the device. So similar thing to what I showed earlier is, we're not waiting around on the host side for these device things to complete. Okay. Last thing is the matrix multiplication, which again, just a stand-in for your actual computation. I spent zero time looking into this, but just doing a bunch of CuPy matrix multiplications. And at that point, like if you needed to, there are additional things for measuring, like, okay, how well am I actually using all the resources of the GPUs, SMs, things like that. Didn't get into that. Wasn't really the point. The point here was like, okay, what are all the steps you need to take such that you actually are even able to utilize the GPU efficiently? Which, just as a summary, in this specific case for this Zarr workload was really, really tight control over memory allocations, including the type of memory, so using pen memory for transfers, being smart about where we do the decompression. So we want to transfer fewer bytes and decompress on the GPU, just since we do have the compute available. Otherwise, the GPU would be like sitting around waiting for our hosts, our CPU to decompress the data. And then using CUDA streams and non-blocking APIs to make sure that you're queuing up enough work that there aren't these idle gaps in the GPU. So all the codes here, if you want to check it out, you can see there. It's under the Zarr example there, along with a few others. But all the codes there. And then, yeah, reach out if you have any questions. And yeah, thanks. Appreciate it.